So now in this video, we're going to protect a couple of 5 volt, 1 watt LED modules from 12 volts right there. So if we put the two of them in series, then we could actually put 10 volts across them. But the 10 volt regulators aren't near as common as the 9 volt regulator. So we got 9 volts right there. When we turn the power on, and you can see the LEDs get pretty bright there, we got about 0.216 amps of current, 216 milliamps of current. So out of that 12 volts, 3 volts is dropped by the regulator, and the rest of the voltage, 9 volts, goes across the load. It limits current as needed to keep the voltage down to 9 volts. Now we have a 5 volt regulator here. We're going to light one of the LEDs, and you're going to see we actually have more current, about 0.279 amps, 279 milliamps of current. Make sure these aren't on very long if you're going to grab them right afterwards. They get hot pretty quickly. And I did make a diagram for this video. So first off, let's look at the 5 volt out. We have a 5 volt regulator here, but we got 12 volts. That's providing the supply voltage. The current going through the regulator, other than a little trickle there, but the regulator, the LED load, and the power supply is all the same. And so we just need to look at that one current we saw at the power supply, 0.277 amps. That's pretty much what was going through the load and the regulator that way, although a little was trickling there. But in any case, we are dropping 7 volts to get 12 out of 5, just to light one LED there. As we saw, we did have 5 volts across it, so we had about 0.277 amps of current flowing through it. So it was emitting light. They come in these TO220 package. They're integrated circuits, even though transistors also come in that same package. So we're dropping 7 out of that 12 volts right there, getting about 277 milliamps of current, 0.277 amps. We're getting almost 2 watts of power, and according to the website I just looked at, more than 2 watts you'd want a heat sink. So we're getting close to that wattage limit. If we start to overheat these integrated circuits, so they actually cut down the current, the output voltage will go down at the same time, but they start limiting current and thus output voltage as needed to prevent themselves from overheating. They have protection circuitry within them. Most components don't, though. Don't assume that they do, even if they're in the same package. So now we have this other circuit. As I said before, one of the ways to deal with that extra voltage there, instead of having putting 5 volts across one of them, just put a couple of them in series, and then they will need 10 volts to turn on fully to get this same amount of current, because each one of them will drop half of that voltage. But the 9 volt regulator is more common, the 7809, so we're going to use that one for this video. And thus, with 9 volts, we had about 0.216 amps of current, 216 milliamps of current going through them. We have the 12 volt supply coming in, 9 volts on the output right there. So it's dropping 3 volts, dropping less than half of the voltage that this one was over here. So we take that voltage times the current. We got about 0.651 watts. So this 7809, the first regulator we looked at, was only getting about as a third of as hot as the 7805. And we were getting almost twice the light coming out of it. So a lot more of the power was going to light, which we can use, and less was going to heating the regulator, compared to just one LED that had 5 volts across it with 12 volts at the supply. Because they both have 12 volts at the supply, they have similar amounts of current, but this one you're getting a lot more light. So you're getting a lot more use out of this circuit than you are with this circuit, even though the power demands are pretty close to the same. So hopefully that helped make it a little more clear how power works in electronics.